Something happened in October of 2025 that most people scrolled past. A chip about the size of a fingernail, sitting inside a refrigerator colder than outer space, ran a calculation 13,000 times faster than the most powerful supercomputers on Earth. Not a little faster, not twice as fast, 13,000 times faster. The result was published in the journal Nature. No competing research team has come forward to challenge it. It is the first time in history that a quantum computer ran a real, useful, verifiable algorithm and left every classical machine completely in the dust. The machine is called Willow. It has 105 qubits. And what it did in October 2025 changes the way scientists think about computing, about chemistry, about medicine, and possibly about the nature of reality itself. Today we are going to break down every single detail of what happened, why it matters, and what comes next. Nothing is dumbed down. Everything is explained from scratch. To understand what Google did, you have to go back to the basics. Your phone, your laptop, every computer you have ever touched works the same way. It stores information as tiny switches. Each switch is either off or on, 0 or 1. That is called a bit. All the words you have ever typed, every photo you have ever taken, every video ever streamed, all of it is just billions of these tiny switches flipping on and off very fast. Classical computers are extraordinary machines, but they have a ceiling. There are problems where the number of possible combinations explodes so fast that no amount of classical processing power can keep up. Imagine you're trying to figure out how a specific molecule behaves inside the human body. That molecule has dozens of atoms. Each atom interacts with every other atom. The number of combinations you have to check grows exponentially. You do not run out of time in minutes or hours. You run out of time in thousands of years, even with the fastest supercomputer that has ever been built. That is where quantum computing comes in. And to understand quantum computing, you need to understand qubits. A qubit is not a regular switch. It does not just sit in a 0 or a 1. Thanks to a property of quantum physics called superposition, a qubit can be 0 and 1 at the same time, until you measure it. The moment you look at it, it snaps to one answer. But while it is running, it holds both. Here's the most important way to think about this. Imagine flipping a coin. A regular computer is like a coin that has already landed. It is heads, that is a 1. Or it is tails, that is a 0. It is settled. A qubit is like a coin that is still spinning in the air. While it spins, it is heads and tails at the same time. Both outcomes simultaneously live inside it. Only when the coin hits the table does it collapse into one answer. That is superposition. That spinning state is where the computing happens. Now imagine 105 of those spinning coins all in the air at the same time. Each qubit in both states, all of them linked together. The number of simultaneous states they can represent is 2 raised to the power of 105. That is a number so large it is hard to write down. It dwarfs the number of atoms in the observable universe. And crucially, the quantum computer does not have to try each possibility one at a time. It processes all of them at once, the way a wave passes through every path in a pond at the same instant. But superposition alone is not what makes quantum computers powerful. There is a second property called entanglement. When 2 qubits are entangled, changing one instantly affects the other, no matter how far apart they are. Einstein famously called this spooky action at a distance. He hated it. He spent years trying to prove it was wrong. He was wrong. Entanglement is real. In Willow's chip, all 105 qubits are entangled together in precise patterns. They do not just operate in parallel. They operate as a single connected system, where each qubit's behavior shapes and is shaped by every other qubit. The result is a machine that can explore an enormous number of possible answers simultaneously, then use a third property, called interference, to cancel out the wrong answers and amplify the right ones. The best analogy is a maze, where instead of trying every path one at a time, you send a wave through all the paths at once, and the wave naturally finds the exit faster. If you value documented science history like this, subscribe. It's the best way to support our work. Also, comment what city you're hearing this from. This script is researched and verified, drawing on Google's published paper in the journal Nature from October 2025, Google's blog post on the quantum echoes algorithm, and technical coverage from outlets including HPC Wire and Computer World. Now back to the story. The story of the Willow chip did not start in 2025. It started in 2012 when a man named Hartmut Neven founded Google Quantum AI. Neven was a computer scientist and neuroscientist who believed that quantum computing was not a distant dream but an engineering problem that could be solved with the right team and enough money. Google gave him the resources. He assembled a team that would eventually grow to around 300 researchers. Their goal was not to build a toy that could solve fake puzzles. Their goal was to build a machine that could do real science that classical computers could not do. The first major milestone came on October 23, 2019. Google published a paper in Nature claiming quantum supremacy. The chip was called Sycamore, It had 53 qubits, all superconducting transmon circuits etched onto a small wafer. Sycamore ran a specific randomized calculation in 200 seconds. Google estimated the same calculation would take the world's fastest supercomputer, at the time 10,000 years. The announcement was enormous. Google CEO Sundar Pichai called it the hello world moment of quantum computing, comparing it to the Wright brothers' first flight at Kitty Hawk in 1903. Brief, impractical, history-changing. IBM, which was building its own quantum computers and had a massive stake in not losing the race, immediately pushed back. IBM's researchers published a rebuttal arguing that with some clever tricks, their own Summit supercomputer at the Oak Ridge National Laboratory in Tennessee, a machine that filled an area the size of 2 basketball courts, could perform the same task in 2.5 days rather than 10,000 years. Scott Aaronson, a theoretical computer scientist at the University of Texas in Austin and one of the most respected voices in the field, acknowledged that IBM's claim looked plausible. The dispute became the biggest argument in computing that year. Neither side fully gave ground, but most independent scientists agreed that even 2.5 days versus 200 seconds was still a meaningful quantum advantage. More importantly, everyone agreed on one thing. The Sycamore result was a proof of concept on a made-up problem. It did not solve anything useful. It demonstrated that quantum hardware could do something classical hardware struggled with, but the task itself, a kind of random circuit sampling, essentially generating random numbers in a very specific quantum way, had no direct real-world application. Google's team knew that. They had said as much in their own paper. The race was now to find the path from quantum supremacy on artificial tasks to quantum advantage on real ones. And there was a brutal problem standing in the way. The problem was errors. Quantum computers are fragile. In a way, classical computers are not. Every qubit in Willow is a tiny electrical circuit. It has to be kept at temperatures near absolute zero, around 10 millikelvin, which is colder than deep outer space, inside a machine called a dilution refrigerator. These refrigerators are enormous. A single quantum computing setup is roughly the size of a room. The dilution refrigerators use a mixture of helium-3 and helium-4, 2 different forms of helium, cycled through a compression and expansion process to reach temperatures that no other natural environment on Earth achieves. At that temperature, the metal in the circuits enters a superconducting state, meaning electricity flows through it with zero resistance, which is what makes the qubits stable enough to maintain their quantum properties at all. Outside these conditions, a qubit's quantum state collapses instantly. A vibration, a stray microwave signal from a cell phone, subatomic particles raining down from outer space called cosmic rays. Any of these can destroy a qubit's calculation. This collapse is called decoherence. It is the fundamental enemy of quantum computing. To fight decoherence, scientists use error correction. The idea is not new. A computer scientist named Peter Shor proposed the basic theory of quantum error correction in 1995. The idea is to spread information from one logical qubit across many physical qubits. If one physical qubit is disturbed, the others still hold the information and the system can recover. But here was the problem that haunted quantum computing for nearly 30 years. Every time you added more physical qubits to correct errors, you also added more opportunities for new errors to creep in. The correction system was making as many mistakes as it was fixing. Researchers called this problem being above the threshold. Below the threshold meant your error correction was actually working. Above it meant you were spinning your wheels. Shor published his theory in 1995. For nearly 3 decades, no quantum computer crossed the line. Every chip, every lab, every billion-dollar research effort hit the same wall. The correction system could not outrun the noise. Researchers tried different types of qubits, trapped ions, which use individual charged atoms suspended in electromagnetic fields, photonic qubits, which encode information in particles of light, nitrogen vacancy centers, which exploit quantum effects in diamond. Each approach had different trade-offs in error rates, coherence times, and connectivity. Google had settled on superconducting transmon qubits, which are among the fastest to operate, but require the most extreme cooling. IBM uses the same basic technology. The race was less about which qubit type would win, and more about which team could engineer their chosen platform to below-threshold error correction first. Willow crossed the line. Google's quantum AI team, working out of their custom fabrication facility in Santa Barbara, California, one of only a handful of facilities in the world built from scratch specifically for quantum chip manufacturing, announced in December 2024 that Willow had achieved below-threshold error correction. They tested it systematically, scaling up from a 3x3 grid of encoded qubits to a 5x5 grid to a 7x7 grid. Each time they added more qubits, the error rate did not rise. It fell exponentially. Each doubling of the grid cut the error rate roughly in half. This was the result that Peter Shor had predicted was theoretically possible back in 1995. It took 29 years to demonstrate it in hardware. The December 2024 results were also when Willow produced the benchmark number that made headlines worldwide. On the random circuit sampling test that Google's Sycamore had first tried in 2019, Willow's performance was almost incomprehensible. Sycamore had done the calculation in 200 seconds when a supercomputer might have taken 10,000 years. Willow did the same benchmark in under 5 minutes. And the equivalent classical computation? Google calculated it would take one of today's fastest supercomputers 10 to the power of 25 years. That is, 10 septillion years. The universe has existed for approximately 13.8 billion years. 10 septillion years is not just longer than the age of the universe, it is longer than the age of the universe multiplied by hundreds of millions of times over. The number had no practical meaning. It was simply the clearest possible statement that classical machines could not compete on this specific task. But there was still the criticism that had followed Sycamore in 2019. The random circuit sampling test had no real-world application. It was a benchmark designed specifically to showcase quantum hardware's strengths. Nobody needed to generate random quantum numbers faster than supercomputers. The world needed quantum computers to help design drugs, to model chemical reactions, to simulate the behavior of materials at the atomic level. And for that, the results had to be verifiable. You had to be able to check that the quantum computer gave you the right answer. This is the deeper problem that most coverage of quantum computing misses entirely. When a classical computer runs a calculation, you can verify the answer independently using a smaller version of the same calculation or by cross-checking with another machine. When a quantum computer runs a calculation on a problem classical computers cannot solve, how do you know the answer is correct? You cannot just run it on a supercomputer to double-check. The whole point is that the problem is too hard for supercomputers. This was called the verifiability problem, and for years, it was the central argument skeptics used to dismiss quantum supremacy claims. Google's 2019 result had a specific weakness that IBM and others pointed to. The results of the Sycamore experiment could not be independently verified using any other quantum computer or any known classical method. The result was, in a technical sense, not reproducible. Willow's team set out to solve the verifiability problem directly. The answer was the algorithm they called quantum echoes. Subscribe if you want more documented science history like this. Comment your city. Back to the story. The quantum echoes algorithm has a formal scientific name that most people will never use. An out-of-time order correlator, or OTOC. Do not worry about the name. Focus on what it does. The algorithm measures something specific and physical about how a disturbance spreads through a quantum system. Imagine you drop a stone in a still pond. The ripples spread outward. If you could play the recording in reverse, you would see ripples converging back to the point where the stone hit, arriving at exactly the right moment to simulate the stone being removed. Quantum echoes does something mathematically similar. Google's team sends a precisely crafted signal through the 105 qubits on Willow's chip. They disturb exactly 1 qubit. Then they reverse the signal's time evolution, running the operations backwards. They listen for the echo, the moment when the disturbance signal comes back amplified, strengthened by a quantum property called constructive interference, where quantum waves add together to become louder instead of canceling out. This process is extraordinary for a specific reason. Because you are reversing the operation step by step, you can verify the result. The strength of the echo tells you whether the quantum operations were performed accurately. If the chip made errors, the echo will be weak or wrong. If the chip ran cleanly, the echo will match the prediction exactly. The verifiability is built into the physics of the experiment itself. You do not need a supercomputer to check the answer. The echo either comes back correctly or it does not. This is a fundamentally different kind of quantum achievement than what Sycamore did in 2019. Sycamore ran a problem designed for quantum computers with no classical equivalent. Nobody could verify the result because no classical machine could reproduce it, and that was partly the point. But it also meant the result lived in a strange position. Technically impressive, practically unverifiable. Quantum echoes flips this entirely. The algorithm is based on a physical process, an echo in a quantum system, that can be studied at small scales on classical computers, or checked against other quantum computers running the same code. The result can be reproduced. Any quantum computer of the same caliber, as Google put it, can run quantum echoes and get the same answer. That reproducibility is what makes the October 2025 result the first truly verifiable quantum advantage in history. This is what happened on October 22, 2025. Google's team ran the quantum echoes algorithm on Willow's 105 qubits. The echo came back. And when they compared the speed of running this algorithm on Willow versus the best available classical algorithm running on one of the world's fastest supercomputers, Willow was 13,000 times faster. The result was published in Nature. No classical computing counterclaim has emerged. No team has stepped forward with a paper showing a classical machine could close the gap. The team measured the performance through 1 trillion individual measurements taken over the course of the entire project. 1 trillion. Google noted that this number represents a significant portion of all measurements ever taken on all quantum computers combined across every lab in the world, going back to the beginning of the field. The speed that made 1 trillion measurements possible was itself a technical achievement. Willow's hardware operates at speeds measured in tens to hundreds of nanoseconds. A nanosecond is 1/1000th of a second. The entire chip's 105 qubits were measured with fidelities, accuracy rates, of 99.97% for single qubit operations, 99.88% for entangling operations, and 99.5% for readout. These numbers are not just high, they are the highest ever achieved at this scale across an entire chip array, operating simultaneously. The Nobel laureate Michel Devoret, serving as Google's chief scientist for quantum hardware, credited Willow's 105 qubit capacity, combined with its remarkably low error rate of 0.1%, as the combination that made the experiment possible. That error rate comparison is striking. In Google's 2019 Sycamore experiment, only about 0.1% of the data gathered was correct. In the 2025 Quantum Echoes experiment, only 0.1% of the data could be wrong. The numbers are mirror images of each other across 6 years of engineering. The team had not just doubled their performance, they had flipped the ratio. To grasp what Quantum Echoes measures, you need to understand why scientists care about how disturbances spread through quantum systems in the first place. The answer is that this spreading, scientists call it quantum information scrambling, is fundamental to understanding many of the deepest unsolved problems in physics. When a qubit is disturbed, the information from that disturbance does not stay in one place. It spreads across all the other qubits, becoming encoded in the collective behavior of the whole system. Physicists studying black holes believe something similar happens when matter falls into a black hole. Information does not disappear. It gets scrambled and distributed across the surface of the black hole in an extraordinarily complex pattern. Studying quantum scrambling in a lab with a controlled chip is, in a sense, studying the same physics that governs some of the most extreme objects in the universe. This is why Google's blog post on the October 2025 result notes that quantum echoes can help scientists understand structures and systems from molecules to magnets to black holes. But the most immediate practical application that Google identified is in chemistry and medicine. Specifically, the team partnered with the University of California, Berkeley, in a collaboration with researcher Ashaka Joy and his team, to run the Quantum Echoes algorithm on Willow to study 2 real molecules. The first had 15 atoms. The second had 28 atoms. Both are small by the standards of pharmaceutical chemistry, but they are real molecules with real quantum mechanical behavior. The team ran the Quantum Echoes algorithm on these molecules and compared their results to a classical technique called nuclear magnetic resonance spectroscopy, which is a standard laboratory method related to the same physics that powers the MRI machines used in hospitals. The quantum results matched the classical NMR results where both could be compared, which validated the approach. But crucially, the quantum measurements also revealed molecular information that standard NMR cannot access, including longer distance measurements within the molecule that are beyond what classical NMR can detect. This is the first time a quantum computer has run a verifiable algorithm on practical molecules and produced information that classical instruments cannot. It is a small step. 15 atoms and 28 atoms are far from the scale of a drug molecule, which might have hundreds or thousands of atoms with vastly more complex interactions. But the scaling behavior is what matters. Classical computers struggling to model molecules hit an exponential wall very quickly. Double the number of atoms and the computation does not take twice as long. It takes many thousands of times longer. Quantum computers, by contrast, grow their capability in ways that map naturally to the physical complexity of molecules. The Quantum Echoes approach, if it scales, could become what Google called a quantum scope, a tool for seeing into molecular structures, the way the telescope opened up astronomy, or the microscope opened up biology. To understand what this means for medicine, consider how drugs are currently discovered. A pharmaceutical company identifies a disease target, usually a protein in the body that is malfunctioning. They need to find a molecule that will bind to that protein and fix the problem. Testing every possible candidate molecule in a lab is extraordinarily expensive and slow, so companies use classical computer simulations to narrow down the list before any lab work begins. These simulations are imperfect because classical computers cannot fully model quantum interactions at the molecular level. They use approximations. Sometimes those approximations are good enough. Sometimes they miss a drug candidate entirely, or worse, they recommend candidates that fail in expensive clinical trials. Quantum computers that can accurately simulate molecular geometry, exactly what Willow demonstrated in October 2025, even at 15 and 28 atoms, represent the beginning of a path toward computer-assisted drug discovery that does not rely on approximations. The same technology could help design better batteries for electric vehicles by modeling the quantum behavior of new electrode materials, or help engineer polymers and industrial chemicals with precisely tailored properties. Hartmut Nevin, the founder of Google Quantum AI, who has run the team since 2012, described the October 2025 result as the first demonstration of verifiable quantum advantage on hardware. not quantum supremacy on an artificial benchmark, verifiable quantum advantage on a practical task. The distinction matters enormously. Quantum supremacy, the term John Preskill coined in 2012, was designed to describe a quantum computer beating a classical computer on any task, no matter how artificial. Quantum advantage means beating classical computers on something actually useful and checking that the answer is right. Getting from supremacy to advantage took 6 years after the Sycamore breakthrough. It required the engineering of a new chip, a new facility, a new fabrication process, a new algorithm, and a collaboration with academic researchers at one of the world's top universities. Google's roadmap, as the company has publicly outlined it, does not end here. The company has already identified its next target, a long-lived logical qubit. The distinction between a physical qubit and a logical qubit is crucial and often lost in popular coverage. A physical qubit is an actual piece of hardware, a tiny circuit on a chip. It makes mistakes, it decoheres, it needs error correction. A logical qubit is an error-corrected unit of quantum information, built from many physical qubits working together. One logical qubit might require dozens or hundreds of physical qubits, depending on how aggressive the error correction needs to be. Willow's below-threshold error correction, achieved in December 2024, is the necessary foundation for building logical qubits. Without it, logical qubits cannot function. With it, the question is just how many physical qubits per logical qubit the system needs, and how long a logical qubit can hold its state without error, its lifetime, measured in microseconds or eventually milliseconds. The race Google is now running is not against classical computers anymore. It is against itself, pushing the lifetime of logical qubits longer and longer, reducing the physical qubit overhead needed per logical qubit, and scaling the number of qubits from 105 toward the millions that would be needed to tackle the deepest problems in science and industry. In Google's own candid words, reaching their ultimate goal will require orders of magnitude improvement in system performance and scale, with millions of components to be developed and matured. They are not promising that is around the corner. They are promising steady, measurable progress along a roadmap they have been executing since 2012. The other major players have not stood still. IBM has been building quantum computers accessible via the cloud since at least 2016 and has mapped out a roadmap of its own. As of 2025, IBM was targeting a 200 logical qubit system they were calling Starling, with a timeline pointing toward 2029. IBM's approach to scaling has involved connecting multiple smaller chips together, linking systems like their 133-qubit Heron processor into larger ensembles, on the theory that managing error zones is easier in a modular architecture than in one giant chip. Microsoft took a different technical path entirely. In February 2025, Microsoft introduced a chip called Majorana 1, which uses a different type of qubit built on so-called topological states, rather than superconducting circuits. Topological qubits, if they work as theorized, would be inherently more resistant to errors because the quantum information is encoded in the global shape of a quantum state rather than in any single physical location on the chip. A localized disturbance cannot disrupt information that is stored globally. Microsoft claimed Majorana 1 represented a path to 1 million qubits on a single chip, though the company acknowledged that the path involved significant engineering challenges yet to be overcome, and that the fundamental topological qubit had not yet demonstrated the same level of verified performance as Google's or IBM's superconducting chips. IonQ, which uses a fundamentally different approach called trapped ions rather than superconducting circuits, demonstrated in March 2025 a 12% speed advantage over classical supercomputers in a simulation related to medical device testing, modest compared to Willow's 13,000 times faster result, but meaningful because trapped ion qubits have certain natural advantages in coherence times and connectivity that make them attractive for specific kinds of algorithms. None of these competitors have published a result matching or exceeding what Willow achieved in October 2025. No classical computing counterclaim has emerged for the quantum echoes demonstration. The scientific community is watching for one. Scott Aronson, who publicly acknowledged IBM's 2019 counterclaim as plausible, has not raised comparable doubts about the 2025 result. The reasons are structural. The quantum echoes algorithm is verifiable in a way that random circuit sampling is not. The echo either comes back or it does not. The verification is built into the physics. There is one more layer to this story that appears in almost no mainstream coverage. It involves the multiverse, and it is not science fiction. When Google's Hartmut Neven discussed the Willow chip's extraordinary performance in late 2024, he made a statement that set the physics community on edge. He suggested that the speed of Willow's computations was consistent with the many worlds interpretation of quantum mechanics. The idea, first developed by physicist Hugh Everett in his 1957 dissertation called The Theory of the Universal Wave Function, that every quantum event that could go multiple ways actually does go multiple ways, branching into parallel realities with each quantum measurement. The British physicist David Deutsch who is among the founding figures of the theory of quantum computing, has argued since at least the 1980s that quantum computers derive their power precisely because they perform computations across multiple branches of reality simultaneously. When you run a quantum algorithm that explores a vast number of possibilities at once, Deutsch argues, those computations are literally happening in parallel universes. The interference between the branches is what produces the answer. Most physicists are careful here. There is no experiment that directly proves the many worlds interpretation is correct. There is also no experiment that rules it out. The physicist Ethan Siegel and others pushed back on Nevin's framing, arguing that quantum computers can be fully explained within a single universe using the mathematical machinery of quantum mechanics without needing to invoke parallel worlds. The competing Copenhagen interpretation, the older and still most widely taught view of quantum physics, says particles simply exist in all possible states until measured, and the apparent weirdness comes from the mathematics, not from actual parallel realities. The debate between these interpretations has been running since the 1920s. Willow did not settle it. But the fact that a working computer operating at the frontier of human technology raises genuine questions about the nature of reality is not a trivial thing. It is worth sitting with. What is not in dispute is what Willow actually did: 105 qubits, fabricated in a custom facility in Santa Barbara, California, cooled to 10 millikelvin inside a dilution refrigerator, a temperature achieved by compressing and expanding a mixture of two different isotopes of helium across multiple cooling stages, reaching a point colder than any natural environment in the known universe. The chip ran an algorithm that sends a signal through all its qubits, perturbs one, reverses the signal, and listens for the echo that comes back amplified by constructive interference. It ran 13,000 times faster than the best available classical algorithm on one of the fastest supercomputers in the world. It produced 1 trillion measurements over the course of the project. It confirmed the molecular structure of a 15-atom and a 28-atom molecule, matching classical measurements and revealing molecular geometry that classical instruments could not see. It was published in Nature. No rebuttal has appeared. The Willow chip took nearly a decade to build. It required a new fabrication facility. It required solving a problem in quantum error correction that had resisted every attempt since 1995. It required a new algorithm designed not just to be fast, but to verify its own answers. It required a partnership with the University of California, Berkeley, to apply that algorithm to real molecules. And it required 1 trillion measurements to be taken at speeds of tens to hundreds of nanoseconds, with accuracy rates above 99.8% across the whole chip. The last milestone before October 2025 was December 2024, when the below-threshold error correction result was announced. The milestone before that was 2023, when the team demonstrated quantum error correction working in principle. The milestone before that was 2019, when Sycamore ran 200 seconds against 10,000 years. Each step forward doubled or tripled the team's capability and revealed the next wall to climb. The wall after quantum echoes is the long-lived logical qubit. After that comes a larger system. After that comes a fault-tolerant quantum computer running algorithms that help design drugs that cannot be designed today. Model materials, whose behavior cannot be predicted today, simulate chemical processes that could unlock cheaper and cleaner industrial production. None of that is here yet. All of it is more reachable today than it was before October 22nd, 2025. Consider the pace of the milestones. In 2019, Google had a chip with 53 qubits and a result no one could fully verify. In 2023, the team demonstrated that quantum error correction could work in principle on their hardware. In 2024, Willow crossed the threshold that Peter Shor had identified in 1995 as theoretically necessary, below threshold error correction, where adding more qubits actually reduces errors rather than increasing them. That result also produced the 10 septillion year benchmark, and in October 2025, the same chip ran a verifiable algorithm 13,000 times faster than the world's best classical machines, on real molecules, with real results that matched and extended what classical instruments could measure. Each of these milestones was separated by roughly 1 to 2 years. The roadmap has been executed on time. The people building Willow are not physicists working in isolation. Google's quantum AI team employs engineers, material scientists, software developers, and cryogenic specialists alongside the theoretical physicists. The fabrication facility in Santa Barbara employs a clean room, an environment where the air is filtered to remove virtually all dust particles, because a single speck of contamination on a qubit circuit can ruin it entirely. The researchers iterate on chip designs, test them in the cryostats, analyze the data, adjust the design, and run again. The fact that Google built its own facility rather than continuing to use shared academic labs, as chief architect Anthony Megrin explained, means that the iteration cycle is faster. An idea can go from the whiteboard to a physical chip tested inside a dilution refrigerator in a fraction of the time it would take if the team had to queue for time at a shared facility. That speed of iteration is itself a competitive advantage, separate from the hardware numbers. 15 atoms, 28 atoms, 105 qubits, 13,000 times faster than the fastest supercomputer. The echo came back.